If a car travels exactly 100 kilometers in exactly 2 hours, it must hit exactly 50 kilometers per hour at some specific point during the trip. This mathematical guarantee is called the mean value theorem. To apply this theorem, we need to establish two strict prerequisites. First, the function representing this trip must be continuous on a closed interval from A to B. This means there are no breaks, jumps, or sudden teleports along the path. Second, the function must be differentiable on the open interval A to B. This ensures there are no sharp corners or jagged spikes, representing infinite physics-breaking changes in velocity. Confirming these two conditions ensures our physical intuition about continuous movement aligns perfectly with mathematical reality. We will start by examining Theorem 5.8 in Rudin's text. This states that if a function reaches a local maximum and a derivative exists at that point, the derivative must be zero. When a curve peaks at a local maximum, it stops increasing and hasn't yet started decreasing. The tangent line at that exact summit is perfectly horizontal. This introduces a concept known as Rolle's theorem. If a continuous curve starts and ends at the exact same height, it is forced to create at least one peak or valley with a slope of 0 in between. This brings us to Theorem 5.9, the generalized mean value theorem. Rudin introduces a complex auxiliary function, h of t. By cross-multiplying the boundary values of f and g, this trick guarantees h at a equals h of b. Because this trick aligns the endpoints so that h of a equals h of b, we can apply our previous rule. Theorem 5.8 activates, guaranteeing there is at least one point where the derivative of h equals 0. This completes the proof of the generalized mean value theorem. Rudin's seemingly random algebraic function is a highly precise lever, designed specifically to exploit the zero-slope rule of Theorem 5.8. We can derive the standard mean value theorem, Theorem 5.10 in the text, directly from this. By setting the second function, g of x, simply equal to x, the complex equation collapses into a clean, familiar formula. Geometrically, this equation ensures that if you draw a secant line between the start and end points of a curve, there must be at least one point, C, on that curve where the tangent line is perfectly parallel. The instantaneous rate of change matches the average rate of change. Let's test this with a concrete problem. Take the function f of x equals x cubed minus x on the closed interval from -1 to 2. Find the point C guaranteed by the theorem. Try pausing here to calculate this yourself. First, we verify the function is continuous and differentiable. The endpoints are f of -1, which is 0, and f of 2, which is 6. The average slope is 6 minus 0 divided by 2 minus -1, giving an average rate of change of 2. The derivative is 3x squared minus 1. Setting this equal to 2 gives x squared equals 1. This yields two mathematical answers, +1 and -1. However, the theorem guarantees a point specifically within the open interval between our endpoints. We must discard the -1, leaving c equals +1 as our only valid solution. The mean value theorem abstractly guarantees that this point exists, but working through the calculation computationally verifies its structural reliability. We can now look at Theorem 5.11. This page shows how the mean value theorem is used to rigorously prove that if a derivative is consistently positive, the function itself is strictly increasing. Without the mean value theorem, we could not actually prove this basic property of functions. It serves as the primary bridge connecting the isolated slope at a single point to the overarching behavior of the entire graph. To review, Rolle's theorem is a specific application where the slope is 0. The standard theorem connects average rates to instantaneous rates. The prerequisites of continuity and differentiability are strict requirements. And finally, these rules form the scaffolding for analyzing functions globally. The mean value theorem reveals a deep connection between local behavior and global behavior of functions, making it a cornerstone of mathematical analysis. If you want more deep and structured explanations from books like Rudin, including every theorem, proof idea, and example, don't forget to like, subscribe, and continue your journey into higher mathematics.